Welcome to lecture 4 on module 1. This is the last session of module 1, which deals with exception and interrupts and the reset sequence. Exception and interrupts. In Cortex M3 processors, we have the NVIC block, which we call it as the nested vectored interrupt controller block, which takes care of the exceptions and interrupts. There are totally 256 exceptions and interrupts that the NVIC block can support. So you have a fixed number of exceptions and interrupts, fixed number of external interrupts. So the Cortex M3 processor can support 15 exceptions and 240 external interrupts. So together it comes up to 256. So these 256 exceptions and interrupts can be handled or supported by the NVIC by giving different priority levels to it, and those levels can even be dynamically reprioritized. Another feature of NVIC is it supports a vectored interrupt, which means that the address of the exception handlers and the ISRs, the address in the memory where the exception handlers and the ISRs are stored, is saved in a table, and that table is what we call it as the vector table. So you have a vector table which will have the addresses, which would contain the addresses of these 256 exceptions and interrupts. Okay, so first let us see the system exceptions. There are 15 exceptions. These are the exception numbers and these are the exception types. Exception number 1 refers to int reset, which is used for running the reset handler. The exception 2 stands for non-maskable interrupt, which means that this interrupt cannot be disabled. It has to be given the highest priority next to reset. Third type of interrupt exception 3 refers to hard fault. So this is actually referring to all classes of fault. So this hard fault exceptions would be raised whenever a particular fault handler is not being executed or handled. So you have an exception being raised, and if the exception handler is not executed due to various reasons, like maybe it has been disabled or masked using the interrupt mask register, then this hard fault exception would be raised, saying that that needs to be serviced. Okay. Next, we have the memory management fault, which basically deals with the memory, and it is an exception raised whenever you have, say, MPU violation or invalid access is made. Fifth interrupt number 5 is the bus fault, which deals with the error in the bus interface. And exception number 6 refers to usage fault, which is basically due to a program error caused by an invalid instruction or invalid state transition attempts. Right? So these are the exceptions from 1 to 6, and from 7 to 10 they are reserved. Exception number 11 refers to SVC, which is the supervisor call. It is a type of a call instruction used to request privileged access of the hardware or the registers. So SVC is basically used for getting into the privileged level, or to get into the privileged to get into the privileged access level. Debug monitor is my exception number 12, which is used for monitoring or taking care of the debug operations, or raising an exception when the various debug operations are in process, like breakpoints, watch points, and so on. Exception number 13 is not used, it has been reserved. Exception number 14 is pendsv, which is a call instruction which is used to switch from one context to another. Example, if you want the processor to switch from sleep mode to some task. Okay, if you want the processor to switch to a task from sleep mode, this pendsv call instruction would be executed. So basically, in ARM Cortex processors, we have sleep mode and even deep sleep modes for saving power. So whenever the processor wants to switch from this sleep mode to a task, this pendsv call instruction would be used to indicate that you have services pending in the queue which needs to be executed. Next, system exception number 15 refers to system tick timer, which is basically a timer to generate the required tick time or the tick interval with respect to which all operations would be synchronized. Next comes the priority levels of these exceptions. So you can see that reset has the highest priority, and then you have the NMI followed by hard fault. So only for these three exceptions you have numbers being assigned, and all other exceptions 4 to 15 are programmable, which means we can decide the priority of these exceptions. So the description of these exceptions is what we have given here. As I already told you, this is non-maskable interrupt. This hard fault is for all fault conditions. This is for the memory. This part is for the bus. This is for the program errors. And SVC is for getting into privileged access level. Debug is for the monitoring the debugging operations. And PendSV is to tell the system that there are services that are pending. And system tick is the system tick timer, which is used for generating the tick time. Right. So these are the exceptions. Now let us see the interrupts. So the interrupts would start from the exception number 16 and it would go up till 255. So totally we would have 0 to 239, which means 240 external interrupts can be serviced by my Cortex M3 processors, and the priority of all these interrupts are programmable. So the programmer can decide the priority and assign the priority for these interrupts for deciding their ISRs being executed. So that's about interrupts and exceptions. Now let us see the vector table of this exceptions and interrupts. So these are the exception times which we just went through. Reset to system tick are exceptions, and then we have the external interrupts, the vector numbers. So a reset starts from 1 and you have the interrupt from 16. It starts at 16 and it would go up till 255. So totally 0 to 255, you have 256 exceptions and interrupts. Coming to the priority, these three are assigned the priority and others are programmable. Now we would be finding the address. Okay, we would be finding the vector address or the address in the vector table from where I can retrieve the exception handler or the ISR address. Okay, so the first location in the memory 00000000 is used for storing the stack pointer value, which we have not shown here because that is not a type of exception. Okay, so the initial location, the starting address is used, the first address is used for storing the stack pointer. Okay, so since we are dealing with 32-bit numbers, since we are dealing with 32-bit addresses, we would require 4 locations to hold one address. Okay, so we would require 4 locations to hold one address. So you can see that the addresses are written in increments of 4. Okay, so the reset vector's address would be stored in the vector table, and in the vector table the address where you have to go and refer is 4. Okay, at this address I will have the reset vector address being stored. Similarly, NMI is at 8, so you can see that all the addresses are incremented by 4 because I would require 4 locations to store every address, which is a 32-bit number. Okay, so if you see the vector table size, it would start with 0 and it would end at 3FF. It would end at 3FF for the 256 exceptions and interrupts, which means that 1 KB of memory is used for holding the vector table. 1 KB of memory is required for storing the vector table alone. Okay. So these are the functions of the NVIC which we have already seen. All these operations are handled for the 256 exceptions and interrupts by this NVIC block. Okay. Last topic of this module, reset sequence. So here we would be learning what are the steps the processor would follow after exiting the reset. Once you press the reset, what are the things that it would go through? So once I press my reset, exits reset, it will go to the first address, that is 0, and at that address you will have the value of the stack pointer, that is R13 value would be initialized there. So the default value of that stack pointer would be read from that particular address. Next, it would go to 4, the next location, it will go to 4. The next word, it will to read the next word, it will go to 4, and there you will have the address of the reset vector. So it will take the address of the reset vector, go to that particular reset address, that particular address, and it would start executing the reset handler, okay, or the program. So with respect to time, if you have to see, after reset, once the reset button is pressed, it will go to this address, the first address, and it would fetch the SP value, stack pointer value. Next, it would go to this address 4, and it would fetch the reset vector. Once the reset vector value is obtained, it will now jump to the reset vector address. Okay, so the PC would change its value to the reset vector address, and it will jump to that particular address, and it would start fetching the instructions from that point, which would be executed by the processor. Okay, so if you have to explain the reset sequence, say you are starting at this address. At this address, I should have, this is the memory. At this address, this refers to the address, and this refers to the data there. So here inside this table, at this location, I should have the value of my stack pointer, right? It should have fetch the value of the stack pointer. If I need to initialize the stack pointer value, I should be very clear with what would be the stack area that I'm going to use in the program. So if suppose this is the stack region, say suppose I want 1 KB of stack. Okay, I would be requiring 1 KB of stack. And if the stack is, say, starting at this address, if the stack is starting at this address, if I require 1 KB of stack, the last address would be, to this value, I would add 3FF. I would add 3FF. So if I add 3FF, I would get the value as this. So from 20007C00 to 20007FFF is my stack. So if this region I have to use as stack, as we have already seen, it is a descending stack in Cortex M3 processor. My stack pointer should point to the next value. If it points here, then it will start storing this data below that, right? So the stack pointer would now point to the next address, that is 20008000. So this is my stack pointer value, which has to be stored here, right? So at this address, I would have the SP value, and this SP value is what has to be would be fetched into the stack pointer to indicate the stack region of the processor, right? So some reset value would be, default value of the stack pointer would be initialized here. Next, we have the next location. In the next location, we told you that you will have the address of the reset vector. So that reset vector address is 101. So from here, it will has to jump to the address wherein it will execute the reset vector, which we call it as the boot code. So the boot code would be executed, which is used for booting the system, and this boot code would be stored at the address 100. So you can see that the address here is 101, but here it is 100. So here the LSB bit is made 1 to indicate that it is a thumb instruction. It is a thumb instruction. So we have made the LSB bit 1, but the actual address where the boot code is stored is 100. So from the second location, you get the address of the reset vector, and you move to that location and you execute the boot code, right? So after this, the other locations in the memory, the initial 1 KB is meant for the exception, right? Meant for the exception and when interrupts, which is nothing but the vector table. So the initial 1 KB memory is meant for that. So you have the other exceptions in these locations, and this part of the memory is used for storage of other types of data. So this would be the reset sequence for Cortex M3 processors. So with this, module 1 is completed. Thank you.